when we think of maximizing, you're gonna use that vertex. So imagine, if you will, I'm gonna do a little bit of a throwback. So if you have an ax squared plus a bx plus c kind of function, remember you can find that vertex, whether it's a max or a min, depends on whether or not this is positive or negative, where you use the negative b over 2a formula or some similar type solution. So I'm just going to throw this out here just to keep you a little bit refreshed on that, and understand that in this case, for example, when we look at number 1, and please make sure you have a handout so that you can follow me. So we are maximizing.
You are recording?
Yep.
Okay.
We are recording. Not make me paranoid, I have to check. Yep. So we are maximizing area. And so I don't know if you remember back in the day when you've done pre-cal, that where they start talking to you about, if I have a perimeter formula, perimeter as we know it is equal to twice the width plus twice the length, and the area formula, which would equal width times length. And what you typically would do is solve for one variable in terms of another. So for example, let's say that my perimeter was 100 and this was equal to twice width plus twice length. The rule of thumb is we would divide all of these by 2 since they're all even. And now I've got a new formula, which is 50 is equal to W plus L. And now I can solve for L or W, doesn't matter, right? So let's say hypothetically I solve for L, and L is now equal to 50 minus W. I now take this and plug it in for L, and that's where my quadratic comes from. And so you'll see that play out in the first formula, where in the first formula I'm going to have W times 50 minus W, which will give me 50W minus W squared. And this is where we employ that concept of the vertex, negative b over 2a. Well, I have the negative b right here, or the b value anyway. And here's the a value, which is -1. Okay, so that's a connection of what we're going to talk about today. And so I just need you to take a moment, look at the details, because they do a lot of refer back to the question kind of thing here. So, you know, I may have a question in front of you and you're noticing that you don't see a formula immediately in front of you, but you forgot to look at the fact that we're referring back to another example, okay? So keep that in mind. So here's question number 1. In question number 1, we are maximizing the area. We know that a homeowner has $320 to spend on building a fence around a rectangular garden. It says 3 sides of the fence are going to be constructed with wire fencing at a cost of $2 per linear foot. The 4th side will be constructed with wood fencing at a cost of $6 a linear foot. They simply want us to find the dimensions and the area of the largest garden that can be enclosed with $320 worth of fencing. So imagine, if you would, the fencing. So here's your $6 fencing. I'll go to refer to my notes, because I get tripped up too. So this is a $6 fencing, a little bit more expensive. And then I've got $2 fencing here. I've got $2 fencing here. And I have $2 fencing here. So let's go back and let's assume this is our perimeter. So if this is, let's call this X and X, and let's call this Y and Y, okay? So if you look at the perimeter, and I'm going to look at it in terms of the cost, this is 6x plus 2x plus 2y plus 2y. So far, nothing special, I hope, right? Pretty straightforward. And so if I bring all of the values together, I know that this is $320 tops total, and that should give me this equivalent to 8x plus 4y. Nothing fancy yet, right? We're good? Could I possibly divide here?
Yeah.
What would you divide by? I think 4. So let's take this, let's divide this by 4, let's divide this by 4, and divide this by 4. Please never make the mistake of starting to, hotspot and just divide by random numbers. It's always the same number. So this gives us y is equal to 80 plus 2x. Now, going back to what I said earlier, remember that the area formula is equal to x times y. So in this case, I have area is equal to x times 80 plus 2x, which results in obviously 80x plus 2x squared. Now let's review another important formula or concept. Is distance or a measure ever negative, technically? No. So we know that whatever we have what's called non-negative. So remember, non-negative values.
Professor, shouldn't it be minus 2x? Yeah.
What did I do?
The x switching to the
Damn it.
the other side.
I forgot that. Now you know why. Are we good now? We have y equals, this is also off. This should be negative. Yeah, because I'm subtracting that, right? So it should be 320 initially plus. That's why I wrote the plus. Okay. So if it's non-negative, here's what we know. We know that this formula, this y formula, 80 minus 2x, has to be greater than or equal to 0. If I solve for this, then I get 80 is greater than or equal to positive 2x, and divide by 2, I end up with x is less than or equal to 40. Do we agree?
Yes.
Okay. Now, based on the question, we want to maximize the region. So in this case, where am I on this one? Yes, so we're here. Just want to make sure I'm not missing anything because I wrote a ton of notes. So we want to maximize the area. We know that a of x, the area of x, is going to equal 80x minus the 2x squared. And that x has to be between 0 and 40. So far, is it registering? Easy to follow me? Okay, good. So we'll take that first derivative, right? Because that's going to give us our rate of change. And that's going to simplify to 80 minus 4x is equal to 0. And when we solve for this, we get 80 is equal to positive 4x. And therefore x is equal to 20, and that 20 is what we refer to as the critical number. All right, and so in this case, we would then argue with y equal to, in the previous solution, y equal to minus 80 minus 2x, where x is 20, then our value 80 minus 2 times 20 means that that value will be 40. So our area, as we maximize this, we would say that area a sub x is in the domain between 0 and 40, And from here, we're basically just stating our conclusion. So we know x is equal to 20. We know because of that y is equal to 40, giving us the dimension. So this is your dimension for your rectangular area. Which, if we multiply it, basically is a maximum area of 800. So max area as a product, 20 times 40 will give us 800 square feet. And obviously we'll have one side of 20-foot fencing. Yeah. How easy is that one? You want to take a moment and read it again and see the steps? Just take it in for 1 second. Make sure you have a handout with the questions on it, because it'll help you put everything together. Does it all marinate together for you? Yeah? All right, let's take a look at, if you don't have further questions or concerns here, let's go to, yeah.
Where'd you get -2? Where'd the negative come from? The 2x plus.
Oh, because mathematically you're moving it around. So you're here, this is where you're asking.
Yeah.
So you're at 320 equals 8x plus 4y. I decided to solve for y, right? So because I solved for y, I subtracted the 8x and moved it over here. So I really have 320 minus 8x is equal to 4y, and then I divided by 4 in all three terms, and this became 80 minus 2x equals y, or y equals, that's where it came from. So I just, sometimes when I'm writing, and I just transferred it as a plus. All right, ready for question 2? Yeah. You can follow the steps, they're fairly easy to follow. All right, so let's look at example 2. Example 2, we are minimizing. This is important to understand, minimizing the perimeter. And this does relate back to example 1. That's why I want to take a pause and make sure that you are with me on example 1. So, reading the question, referred to example 1, the homeowner judges that an area of 800 square feet for the garden is too small and decides to increase the area to 1,250 feet. Obviously square feet. What is the minimum cost of building a fence that will enclose a garden with an area of 1,250 feet? What would the dimensions be? And we will assume that the cost of each of the fencing parts is not changed. So we'll begin with the obvious. So going back to that, we're going to minimize the fact that C is equal to 8x plus 4y. If you don't remember where that came from, I'll bring you back to example 1. I'm in the wrong place. Where is this? Oh, right here. Right here. Remember this?
Yep.
Okay. So in this case, we're leaving the subject to the fact that the area xy is equal to 1,250 feet. So we begin. We're going to solve for this in terms of y. So if I do that, then I'm going to get y is equal to 1,250 feet over x. And so my c of x, or my c of x equation here, Didn't write the x, but here, let's go here. Technically, this is not a c of x yet. Now it is a c of x. This will become 8x plus 4 times 1250 over x. Do you understand why? Okay?
Yeah.
That also tells me that c of x is going to equal 8x plus 5,000 over x. And obviously remember that x has to be greater than 0. You with so far? Yeah. All right. The question is asking us to minimize. So what I'm going to do is I'm going to take this equation and I'm going to restructure it. So notice that I'm starting with the c of x equation. That is equal to 8x plus 5,000 times x to the negative 1. Right? Because what did I do? I brought the x up. Since I'm bringing it up, it's positive down here, but negative up here. The first derivative of x, if I take the first derivative, I'm going to get 8 minus 5,000 over x squared. And this has to be greater than 0, remember that. Technically at this point, if I set this equal to 0, we can start to solve for x as a value. So technically I'm going to move this part of the equation that way. So I'm going to have 8 is equal to 5,000 over x squared. You know, in math, here's a little tidbit, I don't know if you remember this, but like when you have a fraction like this, you know, like if I have 4 is equal to 8 over 2, do you know that I can simply swap these and they still mean the same thing? Where 2 is equal to 8 over 4.
So technically you could have 5,000 over 8 equals x squared.
No, I can swap these two. So this will become x squared. X squared is equal to 5,000 divided by 8. Okay, and if I get away with doing that, then 5,000 divided by 8 is 625. Remember, we're still trying to get that minimized. So in this case, then x squared, or x, is equal to plus or minus square root of 625. But can I have negative distance?
No.
No. So forget about the negative. Just know that when you take a square root, it's always plus or minus of that number. We're just going to ignore the negative. And in this case, we know that x is 25, and we only take the plus part of it, the positive. All right. If I take the second derivative, notice that I'm now taking the second derivative of this equation. Remember, this is initially x squared, so the first derivative, let's go here, is 8 minus 5,000 times x to the negative 2. I'm going to take the second derivative, which is going to yield me positive 10,000. Do you see where I'm getting that from? So this times this, right? Take away 1, so now this becomes x to the negative 3. Does that make sense?
Yeah.
Okay, and guess what I'm going to substitute in here? The 25 itself, because it's going to tell me if it's, remember, the second derivative is all about the concavity, right? If it's either opening up or down. And so since I'm trying to minimize, this results in 10,000 divided by 25 cubed, which is going to give me the absolute minimum in this case. Can someone with a calculator tell me what you get?
For 25 cubed,
Yeah, well, what's 10,000 divided by 25 cubed?
0.64.
Okay, so you get a positive number, right? A small one, but it's still positive, right?
Yeah.
So it's greater than 0, and so based on what we talked about yesterday, we know that this is the absolute minimum. If this is the premise of this question, which you have in front of you, I hope. So the premise of this question is to minimize, and we just found the absolute minimum. Then based on this, we know that c of 25, the original function at 25, is equal to 8 times 25 plus 5,000 over 25. So you should end up with 400 when all is said and done. Can somebody verify that? Because I only have a little measly calculator.
Correct.
All right. So this is 400. And hit resume. I think that was an accident. Weird. Yeah, so you got the 1250. We're dividing that by 25, which is 50. And so that means that the minimum cost, for enclosing an area of 1,250 square feet is $400, given dimensions. Let's go. Dimensions 25 by 50, with one 25-foot side. All right, what do you think about that question? Were you able to get the notes? Everybody wrote everything down? Were you able to follow the example? Yeah.
Did we use the 0.64?
To evaluate if it's an absolute minimum, which it is, because we did get a positive 0.64, and that is greater than 0. If you recall the definition of the use of the second derivative in this case, we know that this is a minimum because it is concave up. And so if you go back to basic parabolas, if I'm smiling, right, but the parabola is face up, we know that the minimum is over here.
Mm-hmm.
All right. So far so good?
Mm-hmm.
Let's look at example 3. I love example 3 because it talks about maximizing revenue. Getting paranoid with this recording. So example 3. We're maximizing revenue. Okay, in that example, do I have it? Okay, here it is. All right, so in this case, it says an office supply company sells X number of permanent markers per year at P dollars per marker. The price demand equation, so this is important. So the price demand equation which is, in this case, P is equal to 10 minus 0.001x. It says, what price should the company charge for the markers to maximize the revenue? And what is the maximum revenue? So we're going to begin with some formulas that we did prior, hopefully to remind you as well. Revenue as a function is equal to the price times demand. And we know that in this case, the R of X is equal to 10 minus 0.001x, all of that times the demand, which is X. So that gives you a new function here where the revenue function is equal to 10x minus 0.001x squared. Again, with the concept of non-negative. So whatever value we have in this price demand equation, this has to be greater than or equal to 0. So keep this in mind. If we solve for that, we will find that X is a value. So if I have 10 minus 0.001x, that has to be greater than or equal to 0. And I solve for X. I'm going to subtract the 10 on, actually I'm going to add the 0.001x on both sides. So I have 10 greater than or equal to 0.001x. So I added it to both sides. And then you're going to divide by 0.001 on both sides. And then you're going to get your X, which your X in this case is going to be less than or equal to 10,000. So we're trying to maximize this, correct? So if we're trying to maximize this, keeping all of these details in mind, it's a lot of steps, I know. So if we're trying to maximize this, you need to keep in mind that that revenue function is equal to 10x minus 0.001x squared. And that value has to be between 0 and 10,000. So we're maximizing. Again, what did we do in the last one? Do you remember? Actually, the last one was minimized, but you still remember the first step? I'll give you a hint. First derivative first. First derivative first. So we do this, we get 10 minus, my bad, minus, and remember it's 2 times this, so it becomes 0.002x. That's your first derivative, which we now solve. If I set this to 0, I'm going to get 10 is equal to 0.002x, and I'm going to divide by 0.002 on both sides. All right, and when you do that, you end up with 5,000. So in this case, X is equal to 10 over 0.002, which gives you 5,000. Okay, now what do you think you're going to do? Check for concavity, yeah. So we're going to take that second derivative, going back to this equation here, and you end up with negative 0.002, and in this case less than 0 for all x. If you recall in the previous one, what did I say? It was what? 0.64 positive. So it's concave up. In this one, what do we get?
Negative, so that means it's
Concave down, so that's why less than 0. So, okay, let's see where I am in this example. Okay, so consider that at this point then the max of r of x, the original function, which is going to be r of 5,000, is approximately 25,000. So you're basically substituting into the original function. And so we can then conclude when demand when the demand is x equals 5,000, the price is 10 minus 0.001 times 5,000, which means that each pen is going to cost $5. So the company will realize a maximum revenue of 25,000 when the price of a marker is $5. Okay, that was a lot of little micro steps also, right? As a question, but I mean, pretty standard. If you notice, we're going first derivative, second derivative, analyzing concavity, which tells us, you know, profit, non-profit, you know, are you throwing money at a bad cause or good cause, you know? And pretty straightforward, because if you look at it on the graph, it's clear as day. You're looking at it. You know, there's a lot of little details to really like sit there and microanalyze it, but fine, you know, it's good to know it. So far, are we okay? Okay, I guess I must have written this one somewhere else. I don't know. I can't find it. So it's all good. It's all good. Breathe. Woosah. I think I did something else here. So it's fine. Oh, it's this one. Never mind. Okay. Example 4. I'm hoping I can get through all of this. Are you still recording for me? Because if you're not, I'm going to scream at you. Okay, we're good. Okay, example 4. Now in example 4, again, we're maximizing profit, so that's another good example. They are asking you to refer back to the question we just did. So the question is saying that the total annual cost of manufacturing X markers for the office is C of X is equal to 5,000 plus 2x. What is the company's maximum profit? This one actually is very quick example. And what should the company charge for each marker and how many markers should be produced. It's actually very easy. Okay, take a look here. So we begin with the profit function. Remember that chapter we did on marginal cost, marginal profit?
Yeah, the profit equals revenue minus.
I need you to really remember that. So let's bring this back. This is basically revenue minus cost. So you basically are looking at P of X is equal to R of X minus C of X. Now we know the revenue from the previous example, right? So that's why I said to you, all of a sudden this is going to pop up. So we know 10x minus 0.001x squared minus that cost function, which is 5,000 plus 2x, which if I distribute the negative, it becomes negative 5,000 minus 2x. Okay. So we are going to maximize that profit function, which for us, okay, so let me just bring you back to this. So this is 10x minus 0.001x squared minus 5,000 minus 2x. So you understand now why I'm about to write 8x, right?
Yeah.
Okay, so I just want to make sure we're going to maximize 8x minus 0.001x squared minus 5,000. Okay, remember that this has to fall between 0 and 10,000. So we're going to take the first derivative. So we're assuming this is the original function. If I do the profit first derivative of the profit function, I'm going to get 8 minus
Negative
sorry
0.0.
0.002 x, and this is equal to 0. So I can solve for x now, right? I think, yeah. So this is going to give me 8 is equal to 0.002 x, and if I divide by that, I think I get I want to say 4,000. Check on your calculators, please. That should be my critical number, by the way. This is the critical number. That's the critical number. If I take the second derivative from here, notice that this differentiates and it gives you negative 0.002, which is less than 0, and this is for all x. So in this case, given the second derivative and its indication, we're going to say since x is equal to 4,000, and that second derivative is, in this case, less than 0, the max is a p of 4,000, which is going to lead you to a profit of 11,000. And you just plug that back into the equation. So using the price demand function, which we do have, so we're using the price demand function equation in example 3 with x equal to 4,000, we find the cost of each pen, or the price of each pen, is 10 minus 0.001 times 4,000 which is approximately $6. So we would basically, based on this, realize a max profit. So max profit occurs, again, just to restate, the max profit occurs. So the max profit is, as we denoted, 11,000. When 4,000 markers are sold at $6. Easy enough. Yeah. Super. Okay, let me see if I can get through 5, 6, 7, and 8. Who do we appreciate? All right. So example 5. So example 5, we're also maximizing profit. We're still referring actually back to example 4. And so they're saying in this one that there is a tax. So the government decides to tax the company in example 4, $2 for each marker produced. Taking into account this additional cost, how many markers should the company manufacture annually to maximize its profit? What is a maximum profit, and how much should the company charge for the markers to realize the maximum profit? So what changed? The cost function is now what? What do you think it is? They're going to tax you $2 for each marker. So think of it as 2x. I believe the original value of the cost function for number 4 was 5,000 plus 2x.
Yeah.
But what am I adding? Another 2x. So now you have 5,000 plus 4x. That's your new cost function, given the $2 tax for each of the pens. Now, what also changes is your profit function, because your profit function, P of x, if you want to write down profit function, may help you. I just call it function f of x. This is going to equal, according to the previous question, it should be 10x minus 0.001 x squared, and we're subtracting the cost function, so it'll be minus 5,000 minus 4x. So again, so when you see me write 6x, it's coming from here. Okay? So this now becomes our new profit function of 6x minus 0.001 x squared minus 5,000. So that's your P of x. So if this is P of x, what do we need? The first derivative. That first derivative is going to result in 6 minus 0.002 x. And we're setting that to 0. So if I set this to 0, I can solve for x by adding this to both sides. So I get 6 is equal to 0.002x, and I'm going to divide by 0.002x. What a mess. What did I just do? On both sides. So you get x is equal to 3,000. That's your first derivative. If I take the second derivative, look what's going to happen. It's not going to be a surprise. You're going to get a negative 0.002, which is less than 0. So according to the question, based on that second derivative, we see clearly that the maximum profit, the maximum P of X, is when we look at P of 3,000, which when we substitute results in 4,000. And that value for the pen, for each pen, is going to be 10 minus 0.001 times 3,000, which is equal to $7. So you're going to increase the price of those pens. Those some expensive pens now. A whole $1. So the company's max profit, just to conclude the statement, the company's max profit is $4,000 when 3,000 of the pens are produced. So I'm going to call them markers, which is what they call them. Are produced. Let me raise this up. And sold at $7. Okay, so that's the gist of that question. Again, do you notice original function, first derivative, second derivative? Once we understand the behavior, we can start analyzing from there. Just the gist of it, basically.
Do you have the word markers spelled twice?
I sure do. You're not seeing double. I might be seeing double at this point.
You have the markers.
What did I say here?
When 3,000 markers are produced and sold at $7. Oh, okay, I see.
Do you know what they call that?
Double vision.
Tired. Teacher is tired.
But you're not wearing a red tie.
What?
Red tie, tired.
Red tie, tired?
Yeah, you're tired. Red tie. Spell tired. Tired. Red tie.
Oh my God, this guy. This guy, I tell you, he's a comedian, I tell you. I love it. All right. Hey, guess what we're doing at number 6? Guess what we're doing to revenue?
Maximizing.
Maximizing. Shocker.
Using the previous.
You have to understand, I went home yesterday from work to work at home online for 2 hours. Then got back in my car and went to tutor for 2 hours to help a friend out with her son. So by the time I got home, and no, I didn't have Starbucks, so I felt so out of place there. I'll tell you guys. I mean, hell, I'll pause the video and I'll